All right, so today we're going to study something called L'Hôpital's rule. It's not La Hospital, it's L'Hôpital. It's French, okay? The French mathematician that came up with this. All right, but before we can get into what exactly L'Hôpital was working on, we need to talk about these things called indeterminate forms. And I had a little to get started with. It seems like a pretty simple question, but I think it's going to spark a little bit of debate this morning. Don't take out your calculator. What's 0 to the 0 power? Come on, it's just a little exponential. What is it? 0 to the 0. 0? You guys all agree with that? No? 1? Nothing. So we've got 3 different answers so far. Some people say 0. Some people say 1. Some people just say, it's nothing. You can't do it. So anybody have a strong opinion about why they chose the one they chose? Or because like I said, it seems simple enough. It's just 0 to the 0. But those people that said that it should be 0, what's your reasoning for that? Why do you think it's 0? Okay. So people that answered 0, 0 to any power, or 0 times anything is always 0. We have this rule that says 0 to the a is 0, right? 0 to any power should always just come out to 0. That looks kind of weird. Let me change my 0 there. All right, fair enough. That makes sense. That seems legit. What about the people that said 1? Why did you say 1? Anything to the 0 power is supposed to be 1, right? We have this other rule that says any number to the 0 is always 1. And then there's probably the people that were like, well, it can't do both at the same time, so screw it. Right? So, and actually the people that said nothing are right. It's because of the fact that it can't follow both these two rules at the same time, right? We can't say that it's 0 and 1 simultaneously. That wouldn't make any sense. It can't be two numbers at the same time. So it's something that we call indeterminate, i.e. I can't determine it. Right? That's what that means. 0 to the 0 is an indeterminate form. Okay? It's not undefined. You can't say that. That's actually something different. It's indeterminate. And I'll give you another example of why you can't technically use the term undefined. There's another indeterminate form. What's 0 divided by 0? Well, there's two rules again, right? We have this rule that says 0 divided by anything is always what? 0. So one might say this is 0. We have another rule that says anything divided by 0 is undefined. So is it 0 or is it undefined? Well, again, it can't be both at the same time. So it's indeterminate. So not undefined, because that was one of the options. It's indeterminate again. Okay? So that's an indeterminate form. We don't know what it is. We can't figure it out. Another indeterminate form, infinity divided by infinity. Okay? Now we're going to get into a little bit of some mind benders here when we start talking more about infinity, because there's some interesting rules that in the past we haven't really talked about so much. But in the limit world, which we're going to get into here in a little bit with this stuff, we can start to do some calculations with infinity that maybe before we couldn't. But that's also indeterminate form, because infinity divided by anything is infinity. And then also anything divided by infinity is 0. When you're talking limits. So again, it doesn't jive. So there's a whole list of these things that we're going to look at, where the problem is, if we try to do a limit and we end up with one of these as our answer, then we don't have a way to calculate that limit. However, L'Hopital's rule provides us with a way to rewrite whatever it is that we're working on in such a way that we don't produce an indeterminate form, but we actually produce a determinate form, which means we can determine what it is. We just have to modify it first before we do it. So we have to check. If we're working on a limit and we end up in one of these bad cases, these indeterminate forms, then we look to see, okay, let's see if we can use L'Hopital's rule to then get us through it by going a different way with it. Okay? But I'm just going to write down all the different indeterminate forms that we might run into, and then we'll start doing some limits, and I'll show you where these things come about and how we can get around it. So we've got, what do we got so far? 0 to the 0, 0 over 0, infinity over infinity, some other ones, infinity times 0. That's indeterminate because anything times infinity is infinity. Anything times 0 is 0. So it doesn't work again, right? Some other ones. This is one that always sparks a lot of debate. At least it has in the past. Infinity minus infinity. What do you guys think that should be? Makes sense, at least logically, it seems like it should be 0, right? So how the heck is that an indeterminate form then? Well, when you're talking about infinity, things get weird. So if you have infinity, infinity is everything, okay? So there's a rule that says infinity minus anything should still be what? Infinity. Okay, infinity minus 2 is infinity. Infinity minus a billion is infinity. So infinity minus even infinity is still infinity. Okay? So is it still infinity? Or we have another rule that says anything minus itself should be 0. So is it 0 or is it infinity? So that technically pulls you into that indeterminate status again for that one too. So let's see. The other ones. Here we go. All right. So we also have 1 to the infinity. Again, seems logical that that one should be 1 because 1 to any power is 1. However, anything to the infinity power is infinity, so that doesn't jive. We already talked about 0 to the 0, and then there's also infinity to the 0. Infinity to any power is infinity. Anything to the 0 power is 1. Again, doesn't work. Okay? So, including this 0 to the 0 that we started with today, these are all our indeterminate forms. So, if we run into a limit where it appears as though one of those is the answer, we got to go back and try again and do something different. Okay, is kind of the story here. So here's what L'Hopital came up with. He was working with indeterminate forms and realized that if a limit comes out to an indeterminate form, and is of the form so limit as n goes to a. It could be, this could be a number, this could be as n goes to infinity, any kind of limit, but it would be a function over a function. Okay, so f of n divided by g of n. So it's not f of x and g of x because we're talking n now because we're doing sequences. But so if it's the limit as n goes to a of f of n over g of n, you've got a rational expression there for your sequence, then he discovered that the following is true. The limit as n approaches a of f of n over g of n is equal to the limit as n approaches a of f prime of n divided by g prime of n. So it's not the derivative of the entire sequence, it's the derivative of the numerator as a function by itself, divided by the derivative of the denominator as a function by itself. Okay? Now be careful with this, though. Okay? The key here is if a limit comes out to an indeterminate form. If that's not the case, this is not a true statement. When I was in college, I'll be honest, I didn't catch on to that, and I did really bad on a test because I just started using L'Hopital's rule for whatever limit I wanted. I'm like, sweet, I can use this all the time. I can keep doing derivatives and break them down and make them simpler, and I was rolling and got a whole bunch of stuff wrong because it's only if it's this indeterminate form situation. Otherwise, it doesn't work. It doesn't work. You start getting things that are completely different from what they're supposed to be. So, anywho, so let me give you an example here then. So let's say we've got we'll keep it with n for now. I could technically make it x, I guess, but so let's do the limit as n goes to 0, and do sine n over n squared. Okay. So, when we were first talking about limits, all the way back in chapter 2, so the first thing that you want to try to do is to see if you can make it a substitution. Okay, because sometimes it's just that easy. You take the number and you plug it in and there's your answer. Okay? So, if I take a 0 and I plug it into this thing, what am I going to get? Am I? It's 0 over 0, right? The sine of 0 is 0. And 0 squared is 0, so I'm ending up with 0 over 0. So this limit, written the way it is right now, is indeterminate, right? I got 0 over 0, I can't do it. It's not actually an answer yet. So what I can do, though, because it's an indeterminate form, I can use L'Hopital's rule then and keep going with it and try again. Okay? So L'Hopital says, if it's of f of n over g of n, which it certainly is, right? Your f of n is the sine, your g of n is the n squared, then I can do the derivative of the top and the derivative of the bottom and then try again. Okay? So this would then become limit as n approaches 0 of what? Mm-hmm. But again, only works because it's an indeterminate form to begin with. Okay? So now let's try again. Substitute it again. What do you get? Well, we get cosine of 0, which is what? 1. 2 times 0 is 0. Okay, so I get 1 over 0. Now here's where this kind of math only works when you're talking limits, okay? But 1 divided by 0, normally you would say undefined, right? And you can't divide by 0. Now it's infinity. Because I'm not trying to actually divide by 0. I'm thinking as n approaches 0, what's happening to the overall value of it, it's getting closer and closer to, it's going up to infinity. So this limit should approach infinity. Okay? So, I'm going to since we're talking about it right here, I'm going to go off to the side for just a second because this seems like kind of fuzzy math a little bit, but like I said, in the limit world, you can do this. In general, any number with limits divided by 0, you can consider infinity. Okay, if some of my professors saw me actually writing a divided by 0 equals infinity, they would cringe, but it's just with limits, okay? So as your limit calculation is coming out that way, then that's okay. Also, if you have any number divided by infinity, what do you suppose that comes out to then? 0. So kind of keep these in your back pocket if you run across situations like that as you're doing your work. With limits, that's okay. You can do that. So, all right. So let's try another one of these. Let's do the limit as, and we'll go to x. We can do that too. Technically, this works for all limits, not just those that are written as sequences. So we'll do x going to infinity, 5x squared minus 3x over x squared plus 2. Now, these kinds of limits, you've kind of already done before. Okay? In this one, you might be able to take a look at it and just tell me the answer. I don't know if you remember that little trick we talked about before. It's been a little while. But I want to know, what is the limit to this function as x goes to infinity of 5x squared minus 3x over x squared plus 2? It's really like finding a horizontal asymptote again, right? Does anybody know what the answer to this is then, just by looking at it? Should be 5. Now I'm going to show you how L'Hopital's rule still gets this one done, though. Okay? So you don't have to remember all those little rules. You can just keep doing L'Hopital. As it stands right now, what kind of form are we in? What kind of indeterminate form would we get if we tried to substitute into this thing? Right. So a lot of your homework questions, the first thing they're going to have you do is identify the form. Okay, so that first example we did, it was a 0 over 0 form. This is an infinity over infinity form. And so since we know we have that indeterminate form, so now we can start applying L'Hopital's rule. So we would get limit as x goes to infinity. Derivative of the top would be 10x minus 3. Derivative of the bottom would be 2x. Okay, so again, can I put an infinity into that? Not yet. Okay? So I'm still stuck. I still have an infinity over infinity form here, right? Okay. There's nothing that says you can't keep using L'Hopital's rule as many times as you need, though. So we can do it again, okay, because we're still stuck at infinity over infinity after that step. So, all right, one more time. Derivative of the top would be 10. Derivative of the bottom would be 2. Limit as x goes to infinity of 10 over 2. That's 5. Okay? So whether you're just thinking about the horizontal asymptote here, because this is an x goes to infinity, so you can think horizontal asymptotes with that. You could just look at this and say, oh yeah, I remember that we just looked at the leading terms of these two. Since it's the same degree, it's going to be 5 over 1, so it's just 5. But L'Hopital's rule kind of confirms that for you, though. So as you go through, derivative, okay, 10 over 2, 5. Same thing. Okay? So that still works. All right. So what about some of these other ones? So far we've only dealt with 0 over 0 and infinity over infinity. There's all these other weird-looking ones. It's going to be a little bit tricky with some of these, especially the ones that end up being looking like exponential, like the power ones, because we're going to have to do a little bit of manipulation to rewrite them. Because remember, L'Hopital's rule only works if it looks like this. It's got to look like a fraction, right? And these guys certainly don't look like fractions. So we got to figure out how can we manipulate them before we actually use L'Hopital's rule to make it look like a fraction so we can then move forward with it and do something. Okay? So, let's try one like that. Alright, so let's try this one. Limit as x goes to infinity of the natural log of x to the 1 over x. So, identify that form for me. What do we got? What kind of indeterminate form are we looking at this time? You are close. Not quite, though. It's not 0 to 0. Think about what the graph of natural log looks like. What's the natural log of infinity? Essentially, infinity. It's an increasing function, right? Even though it kind of levels off, as x goes to infinity, this thing still keeps going up, right? So it's still infinity. So what form do I actually have then? Yes, it's infinity to the 0. Okay, so I need to somehow, like I said, rewrite this thing so it looks like a fraction. Well, one trick that you can do, you got that exponent up there, that 1 over x, and I want to get that out of there, okay? I don't want to have an exponent anymore. I want to have something divided by something. Well, there's a rule, there's a property of logarithms that says if you have a power on something that's inside of a log, you can bring that power down. Okay, it's called the power rule of logarithms. So if you had like log base b of a to the c, then you can bring the c down, c times the log base b of a. You guys all remember that little property? Okay, so here's the problem, though, with this one. It seems like, oh, good, I got a log right there. It's raised to a power. I can just bring this thing down next to it. The problem with the way that this is written, though, is this power is not on the x, right? This power is on the entire log. This property only works if the power is on what's on the inside of the log, not the entire thing. So I still can't technically use this, at least not right off the bat here. So what we're going to do is, it's going to seem like cheating at first, but we're going to make sure we cover our butts later. We're going to log the equation. Okay? So we're going to log the whole thing. As long as we unlog it at the end, it works. So we're going to turn this into the limit as x goes to infinity of the natural log of x to the 1 over x. Okay, see the difference? I took a log of the whole thing I started with. Now that 1 over x is on the inside part, right? Because the inside of this log is this. So I can now bring this down in front. See the difference? Does that make sense? Because that's a very important detail. Okay? So, all right. So if I do that, yeah. Wait, this would be the natural log of the natural log of x. Yeah. Okay, like that. So do you guys see how I can now turn this into a fraction? So, instead of multiplying by 1 over x, I can divide by x. And because what I started with was an indeterminate form, this should be still 2. We got to verify that, though, real quick. Okay? So it's either a 0 over 0 or it's an infinity over infinity. That's kind of what we're trying to do with these. Any indeterminate form that's not one of those two, we're going to manipulate it like we did here and then try to get it to be one of those two, because that verifies that, yep, we can still do this. So if I put an infinity into the top of this, if I put an infinity into the bottom of this, what indeterminate form am I left with here now? Mm-hmm. Yeah, exactly. We got an infinity over infinity now. So that means, again, L'Hopital's rule's in play. So I can use that on this to help me out. Okay, so derivative of the top. What's the derivative of a natural log? 1 over x. Okay, so I got a natural log of a natural log. So instead of 1 over x, what is it? Mm-hmm. 1 over natural log x, but it's a chain rule, right? Because I got a natural log inside of there. So I need to multiply that by the derivative of the inside, which is just 1 over x, right? And then all that divided by the derivative of x, which is 1. All right, so let's cinch that up a little bit here. So this is going to be the limit as x goes to infinity of 1 over x natural log x. Okay, so if I try to plug in infinity, what's going to happen here? It'd be 0, right? Because this would essentially be 1 over infinity, right? In which we talked about in the limit world, you can assume that that's actually 0. Okay? Now, that's not our answer. Remember what we did to get this thing started? We logged it. So this function that we were working with this whole time was not actually the limit that we wanted to figure out. But, like I said, if we log it, then we have to undo that at the end, and we're still okay. So what's the opposite of logging something? How do you undo a log? Shut up. What's the opposite operation of doing a logarithm? The inverse of a log starts with an e. Exponential, right? E to the x. So I start by logging it, but then to finish it up, I have to e it, right? So it's going to be e raised to my answer. Okay, e to the 0 is 1. So the answer to this limit is actually 1. Okay, so like I said, as long as we're undoing what we did to get it there and using L'Hopital's rule to get us through the intermediate stuff there, doable. It's doable. So let's try another one here together. All right, again, I'd like you to start by identifying the form of that one for me. We got the limit as x goes to infinity of x tangent 1 over x. Perfect. Yes. All right. So it's not the 0 over 0 or infinity over infinity. So I need to rewrite this thing as a fraction. Now, this one, I don't have to go to quite the lengths that I did on the last one because it's not some kind of exponential, and it's just a multiplication of two things. And I can turn multiplications into divisions pretty easily using reciprocals. So any ideas how I could rewrite this x times tangent 1 over x to make it a division of two things instead of a multiplication of two things? That would work. Wasn't what I was thinking, but oh, then you'd have you'd have infinity over infinity then. So that would work. That's not the way I did it before. Let's try it though. I'm interested. I think maybe that'll work. What I was thinking was take tangent 1 over x and then divide it by 1 over x. Instead of multiplying by x, you divide by 1 over x. But you might be onto something, so let's see. Just curious. All right, so right now then, do it this way. What form am I looking at? Is this a 0 over 0, or is this infinity over infinity, or? You multiply, he just multiplied it by x over x. Oh, you know what? I don't think this is going to work. Yeah, if you take a look at it, I don't have a 0 over 0 or infinity over infinity because the top of this is still 0 times infinity, right? Right, which is not 0, so be careful, everybody. So, yeah, that would be, this is complicating it a little bit. So that's actually not going to work, so sorry. Thought it was worth a shot, but it doesn't go anywhere. So, like I said, what I was thinking, I'm pretty sure this will work, is if we do a limit as x goes to infinity, instead of multiplying by x, divide by its reciprocal. Now, we don't typically do this because in math, we usually want to make things simpler, and this is certainly making it more complex to look at, right? But can you guys all see how that is still equivalent to what we started with? Dividing by the reciprocal is the same as just the multiplying, right? So, okay, so as it stands now, what form am I looking at? I got tangent of 1 over x divided by 1 over x. That's a 0 over 0. Okay, so now we're ready to go, right? We've got one of the two forms we can use. Okay, so I can use the L'Hopital's rule. So do the derivative of the top and the derivative of the bottom. All right, so tangent of 1 over x. What's the derivative of tangent? Secant squared, okay. That's secant squared 1 over x, but then I have to multiply that by the derivative of 1 over x because it's a chain rule, right? What's the derivative of 1 over x? Or negative 1 over x squared? Yep. Okay, so that's the numerator. So the denominator, what's the derivative of 1 over x? Same thing. Okay, so what's going to happen then? Get a little cancellation going on, which is nice. So I got the limit as x goes to infinity of secant squared 1 over x. Okay, so if I try to plug in an infinity, I can actually do it now. Okay, so this would be secant squared of what, technically? 0, yeah. Okay, and secant squared of 0 is 1 over cosine squared 0. What's that going to come out to then? Yeah, because cosine of 0 is 1 over 1 squared is still 1. Done. And I don't have to undo anything this time, right? Because I didn't have to log what I started with to get it going. I just rewrote how it looked, and yeah, so it should still be equivalent. So, yeah, good. So, that's the idea. Now, I'm going to warn you, some of these in your homework are a little challenging, okay? It's not a cookie-cutter method all the time. There's some of these, you have to kind of be a little creative in how you're rewriting things to get it to work, right? Remember, we're aiming for 0 over 0 or infinity over infinity. Sometimes it's going to be the whole log it thing. In general, if you see something exponential, you're going to want to try and go this route. Sometimes it's just manipulating what you have in such a way that it just looks a little different so it's a fraction. But if you can get it in that fraction look and make it 0 over 0 or infinity over infinity, then you're rolling. Okay, that's usually the tough part. If you can get it to that point and go, then you're good. So, all right, well, I'm going to let you guys take a look here. We still got like, I don't know, 25 minutes, so get a little ways into it here.